Right, welcome again, everybody. Today we're going to look at a signal and signal sampling in particular. We will do a little bit of online analysis as well as look at sampling modes and some of the automation functions within the Signal program. As you can see here, I'm running Signal 706, which should be out any day now. This splash screen also tells me that we're up to date compared to what is available on our website. And I don't know whether I mentioned before in a Signal session, but down at the bottom there, it tells us which 1401 and driver we're using. Now, if there are an asterisk at the end here, or two asterisks, then it would indicate that the software or firmware of the 1401 is out of date and should be updated from our website. Okay, so let's move on. So, signal, an oscilloscope. It depends on a trigger of some description. Now, that could be an external pulse coming through from a stimulator, an external stimulator. It could be a trigger pulse, or rather, yes, a trigger pulse from the 1401 itself. So outputs will trigger a frame of data capture. It could also be simply timed by the clock inside of the 1401 hardware, which we use for data acquisition. Okay, so let's have a look at some of the sampling modes here. And when we get to the sample pull down and sampling configuration, we see many different sample modes from basic through to gap-free. Now, a number of these aren't generally used. Some become rather specialized, but I would imagine that you're looking either at basic, peri-trigger, or fixed interval. Usually. I'll go and give you some idea of what the other modes are in a moment too, but let's start with basic. If I were now to open up an XY view, new XY view, and I'll just throw into it a little image. So I'm doing channel image and fill the rectangle and browse. That's going to be basic. Okay, so actually fill background. Close. Okay, what we're seeing here is essentially what happens in the basic sampling mode. So you can imagine at the bottom here in black, we have a trigger, a TTL pulse, which is delivered to the front panel trigger input. Now, a basic sweep would then react to the edge, rising edge in this case, of the TTL pulse, and we will capture to disk this blue section of this line. Okay, so here's a red waveform representing some sort of response or signal we capture at the trigger time. Now, the outputs generated by the 1401 can also follow this same basic 1 or so seconds of data capture. So they start at the trigger point as well and continue on. So we're having a ramp, a square wave, and we finish off with the waveform being low. I say waveform, it could be digital pulses and waveforms that we're producing. We then have a wait time. There will be some moments before a trigger pulse comes out. There could be some months before another trigger pulse is detected. But Signal is sitting there waiting for this trigger to occur. You'll notice in the second version of this, I still have the blue line. That's the recorded area. We still have a waveform, which is the response, as it were, in that recorded area. And I've changed the output. Now, the change in output is represented by what we call states in Signal. So we have frames of data capture. That's what we're writing to disk, preferably. And then we have states that exist in and around those sweeps or frames of data that control the outputs, digital and analog signals for control of other devices. Okay, so let's just minimize that for a second. And if we sample in basic mode, I have simply a trigger, and as long as the trigger is on in the sampling controls here, now this is a dockable toolbar, there we go. I'm not writing to disk in this instance, and I'm not pausing at sweep end. Let's start. Now we're waiting for that trigger. This trigger button is connected to the trigger input on the front of the 41 and is acting just like we're getting a pulse from a magnetic stimulator, an electrical stimulator, or some other device that can deliver a TTL pulse. So there we go, trigger pulse down, and we receive a sweep of data. Home and end to expand out to the maximum of the ADC range, and end to zoom in. Okay, another trigger just to prove. There we go. Now, 0 is at the left-hand edge of the sweep. That's when the trigger occurred. But that doesn't have to be the case. We can, through the sampling configuration, move the position of 0 using the x-axis offset here. So if I wanted to show a supposed pre-trigger time, now remember it's not pre-trigger, we are capturing data only from the single trigger pulse. But if I wanted to relabel the 0 position, I can put 0.1 in here. Now to capture peri-trigger data, we'd move to this mode. Now, when we accept the peri-trigger as the sweep mode, a peri-trigger tab appears. Now, you must be aware that if we use an x-axis offset here, it is compounded by the pre-trigger time that we set here. So in this case, on an event input, a TTL pulse from another device, we are capturing a pre-trigger time, and automatically 0 has been shifted to that 100 milliseconds into the sweep. The sweep length being the frame length here, 1 second. So we're now looking at 900 milliseconds post and 100 milliseconds pre. Okay, so we'll use the event trigger for the moment and run now. Again, the dockable toolbar, trigger is on, start. So we're waiting for a trigger. You can see the 0 position is now here. Get rid of this cursor. Okay. So again, trigger press and end. Once again, there we go. So we're capturing pre-trigger data into memory inside of the 1401. It's there buffered in a circular buffer. When the trigger pulse comes through, detected by the 1401, we keep the 100 milliseconds we've asked for before the trigger, and we continue on for the rest of the sweep of 1 second. Then the data is transferred from memory to the computer, and gives us the ability to view what's going on. Okay, so we have peri-trigger. I think we want to look at the other modes here. So in peri-trigger, we have analog plus, minus, equals, and we have digital modes, as well as the simple event input. Now, if we use an analog input, we'll set to analog plus and set a threshold level. I'll leave it at 0 just for the moment and go run now. Okay. This time, what you see is 2 cursors, trigger above and arm below, acting as a hysteresis there. We need a waveform to pass through the arm below, pass above the trigger above for it to trigger a sweep of data, and then go back down below the arm below. Okay, and we'll show that off in just a second. Now, Right, just a quick question, which is J1 asks, is it possible to jitter the pre-trigger time? Not that I can think of, not in that straight peri-trigger mode. We can jitter the position of frames around, and we'll look at that in a lot of detail later. But I can't think of a way that we could expand or contract the pre-trigger time at this point, but I can certainly get back to you about that. Okay, so I'm just going to switch over a cable here. Right. So I have from the other day a recording of spikes, and I'm going to use that as a trigger for this sweep. Now, if I switch off the trigger and we're not writing to disk, we can simply monitor what's going on. And we start. There we go. So we have some spiking data. Now this is a little undersampled, but it allows me to set my positions for arm above and arm below. I'm dragging with a control, allows me to see what's happening as I drag the y-axis. Okay, and now if we switch the trigger on, we wait, there we go. So we have triggers whenever, I should minimize that, actually set a wide hysteresis here. Okay, so there we go. You should see at 0, we've always got this crossing. Okay, so you imagine this could be used with something like a force plate, a heel strike. So we don't know when it's going to happen. The waveform goes high or perhaps it even goes negative. And we can use these trigger levels to discriminate the data to a degree. When the trigger is achieved in a positive direction, negative direction, or perhaps either, then we would say that's the 0 point, capture the 100 milliseconds or so that we've asked for, and continue on for the rest of the sweep length. So that's peri-trigger mode. Let's throw this all away. I must add that the peri-trigger mode in the waveform sense, that is positive analog, negative analog, etc., works on the last port in the ADC port list. So if I reverse this list, so I wish to capture 2 channels and I have ports 1 and 0, it would be 0 that acts as the trigger input channel, for want of a better description. Now, while we're here, ADC ports, we could describe the ADC ports as a list like so. So ports 1 to 8 inclusive and 12. Usually with something like a micro, you might say 0 to 3. So that's all 4 of the front panel ports on the base unit. 0 to 8 or 0 to 15 for the power base unit. Right, a little more about the sample rate, frame length, and frame points here before we carry on with the other modes. As I mentioned, we're undersampling there for the spiking data that came through. Probably 10 kilohertz would be better. And as I change the sampling rate, you'll see that frame points will update to match. We can then increase or decrease our overall frame length. So that's the frame or sweep width that we're capturing. Let's go to an extended mode here. So, okay, once again, new XY document. And again, I'm just going to throw in a quick picture into the background. Extended. Okay. close. Right, so I mentioned triggers. Triggers being a TTL pulse from a magnetic stimulator, an electrical stimulator, a foot pedal, anything that can produce a switch closure for us, and we can capture data around or from that time point. We have triggers as waveforms, as you've just seen in the peri-trigger mode. So a waveform that reaches 1.1 units, we've set a threshold level, the data that sweep is triggered at that point. Now here, though, we're using the 1401 outputs as the trigger. So the green trace that you see at the top here, that is running. And we might say that after so many changes in the waveform, there is a point here where we wish to capture a data sweep. The control pulses, the controlled stimuli, waveform outputs, digital, etc., can continue on throughout this area into the non-sampled area and again onto the next frame as well, where the same digital output train will trigger internally the time for the next sweep. Now, in that mode, we lose any concept of triggering on the waveform. Okay. So we'll have a look at that in just a second. I'm just going to revert this back to another image, which is the peri-trigger again, and just to clear up the fact that we are waiting for a trigger pulse, external pulse or a waveform to go above the level. That's fine, we've got a data sweep. In this case, the digital and analog outputs can only start operating from the 0 position. Of course, we know nothing, we can't do anything about providing pulses before that trigger because we don't know when it's going to occur. So that's the green line representing analog and digital outputs only after the trigger has been achieved. Now notice it does not continue in the non-captured area here, unlike extended. So I hope that just reinforces things there. Okay, so what happens with extended then? Let's move to extended and everything's fine there. We go to outputs because now we've got to define a set of pulses which are going to be delivered before, during and possibly after a sweep of data. I'm going to choose an analog and a digital pulse here. I'm setting a low resolution for the moment, and we configure stretchable dialog, the graphical sequencer, and I'm going to say that this is 10 seconds long. So that's the output track that I've got, 10 seconds. And I'm going to set the frame of data capture of 1 second duration to be at 5 seconds into the outputs. And this gives me a chance now to put in example pulses. So we've got 20 pulses. We've got a single pulse somewhere in the frame time. And then I'm going to set slower pulses afterwards. So a length, 0.02. And we'll set a bigger interval there. There we go, and we'll get 10 of those in that space. Oops, no, we won't. 6 of those. Okay, so now, as you can see, it's the outputs that are going to trigger our frame of data capture. These pulses will appear, then we'll see a single pulse recorded with the sweep, and then 5, 6 pulses to follow at a slower rate. Okay, so they'll be on for longer. So I need to connect the digital output that I'm using, the digital output BNC on the front panel, and that's feeding port 0 of the Power 1401 that I have here. Let's say OK to that and run now. Let's make this as large as I can on the screen and start. No trigger in this case. Okay, now I'll restart that. Now restart throws away all of the data you had previously, and that's because I wanted to get ready with this. So I've simply got an LED connected through the BNC to the digital output. So this will light up, showing us the pulses are happening before the sweep is captured, and then again afterwards. So if we start now, there's our pulses. We'll then have a break. Then the pulse that exists in the sweep, and then several slow pulses to finish. And then we repeat. So we should be getting a new sweep anytime now. There we go. So it's the pulses in our outputs which are now controlling our sweep timing. Now, of course, we can also have a trigger to start our outputs as well. So if I were to use the switch, we should see our outputs again. There we go. Right. So let's try this. So the trigger pulse first to start the sweep, or start the outputs. Now the output's playing. Short break, frame, end of frame, more pulses. That's it. Okay, so let's stop that. Now you'll notice if I've said stop, I have two buttons that appear. More, perhaps I have some frames that didn't achieve the right quality of capture. That is, TMS-wise, the coil or the subject moved. So therefore I can press more and continue on to gather a few more sweeps. And if I'm completely finished, I'll hit finish now and save the data. Back to the general tab of the parameters, and we're moving on from peri-trigger extended to fixed interval. So what is fixed interval? This is really where we're going to start adding jitter in terms of time. Not a jitter necessarily in terms of the frame length, although I'll show you something there in a second. But we are now using the internal clock to say capture a sweep, capture a frame of data capture with pulses inside it. We'll then wait for, say, 5 seconds and then capture another frame. But that wait time of 5 seconds could be added to and subtracted from a percentage would vary. So we say 50% of 5 seconds can be subtracted or added to that 5 second fixed value to get a time jitter. And we'll look at that in just a second. If we go to, oops, I should have selected fixed interval. So if we now go to outputs and configure pulses again, here we have the same layout as before, but you'll see that in addition to the outputs length and the trigger time, we have an interval rather, and a vary percent. So I'll make things a little simpler. I'm going to drag these pulses off the screen, there and there, and this one. I'm going to set this trigger time to 0, and I'm going to reduce my frame length to 0. So the thick blue line represents the recorded area. I'll set a pair of pulses here and one at the end here, which is shorter duration. Okay, just so we can understand what's going on. So clicking on the blue line, our output length, the trigger for the sweep is at 0 time, and we're going to have a 5 second interval and a 50% variation about that interval time. Let's say OK. We're still running in a mode which is not multiple frame states. So let's run now. I'll just make that slightly smaller and introduce the first of some online analysis. And this is just going to be a trend plot. And we're going to plot the frame number versus the frame time, absolute frame time. New, all filed frames. Now, if it's all filed frames, that means they must be written to disk, which means I must be writing to disk here. Otherwise, I could say all sampled frames or all frames of a certain state. We'll get into states very quickly. So all filed frames for the moment, and no frame subset. So we say OK. So if we had a fixed interval, we would expect to see the first frame of data capture at time 0, the next at 5 seconds, etc., etc. So let's start that. There we go. That's frame 1, 0. Now we're seeing 7 seconds, slightly over 7 seconds. There we have 7 to 11, so 4 and a bit seconds. So it's certainly not a straight line. Okay, so we're getting some variation in time there. And that was all I really wanted to show you there. Import that, and back to the sampling configuration. Okay, so General tab. So we've looked at basic, fixed interval, extended, and peri-trigger. Before we get on to fixed interval and fast triggers, I think we'll go back to basic. And I'll just show you a feature which few people actually use in physiology, but if you don't know it's there, you won't be able to implement it if needed. So what I've got is a signal generator, and it's set to virtually no output at the moment. I'm asking for to use ADC external convert. Immediately, the x-axis units have changed to points, because we have no concept of sampling rate now. External convert means that we're receiving TTL pulses to the event port on the back of the 1401, which is this port here. Okay. Now, your usual digital inputs and outputs would be accepted through this port and this port here. The event port is rather special in that it provides clocks, etc., for other uses. So setting use ADC external convert, we are going to run now, but I'll just be sure and switch off any outputs. Run now. Okay, so no trigger in this case. I'm just going to start, but nothing happens. Okay? No data appears. And that's because we're not receiving TTL pulses at the external convert. Okay, I should set that up a little wider. And there we go. You see the data is speeding up a little, and I can slow it right down because the number of TTL pulses per second is very small. Speeding up again and slowing down. Okay, why? Why use it? Well, in the past we've used systems like that to look at rotating machinery. So you would take a sample at every tooth of a gear, for example. Now translating that to physiology, you might want to look at, say, forces at every tooth on a crank on a bicycle, for example. It's not very often used, but to know it's there, I think, is a good thing. Let's abort that. Sampling configuration again. Okay, so really, we've got extended fixed interval fast triggers. Imagine now a basic mode where we're just getting a lot of TTL pulses coming through per second, which means that we're going to have to reduce this frame size, frame width, to suit. So a common requirement for fast triggers would be stimulating the vagus nerves, where you might have 100 or so stimulations per second. Frame length has to be smaller. We just prepare the next sweep ready for data capture again as quickly as we can. There are some losses when using a mode like this or fast fixed intervals, and those could be the lack of a digital channel, lack of outputs, etc., because we can't get everything ready in time for the next sweep. So since I've mentioned digital channel here, you've got on the right two types of marker. Keyboard, which I personally think is not very useful at all, certainly online and with small duration sweeps. That's because it's difficult to place a marker accurately manually. But the digital channel is very useful, and that can provide information from a separate computer, delivering codes to us. So a bit pattern, which is then translated by the 41 into hex code that we'd see on the screen. Now, we could also connect the trigger output of a magnetic stimulator, for example, and that could be fed to pin 23 of the digital inputs on the rear panel. And that's a strobe line. That says that there's data, and we can cause the signal program N41 to read the data at that point, leaving behind a marker. And that would save having to record these TTL pulses from the magnetic stimulator or other stimulator as a waveform, which is just costly in terms of disk space. So fast fast triggers and fast fixed interval. Gap-free mode. It's trying to be a chart recorder. It's trying to be Spike 2 in this case, where you want to record for a long time with no loss of data. Now, considering that Signal works on a page-by-page basis, this book has no leaves missing. One page from 0 to 1 second, second page from 1.001 seconds to 2, etc., etc. We should not be losing any data, but it's still in a book form, page after page of data. Right, so let's up the ante a little bit and look now at the fixed interval mode, which is one that many people would use. And I think we'll go and set an x-axis offset of, say, 0.2 seconds. Okay, now if we do that, we want to deliver a pulse from the 41 at a logical 0. So x-axis offset at 200 milliseconds is now our 0 position. So in our outputs, we might use the pulses as opposed to the sequencer. We'll come back to sequencer in a minute. Pulses, a DAC, and digital outputs. Now, I know many of you would be interested in magnetic stimulation, so we'd probably be looking at single and paired pulses. If we wanted to apply electrical stimulation as well, a third stimulation channel might be required. Some magnetic stimulators can be controlled in an analog form. So I can change the analog waveform here, DAC 0, producing a waveform output, perhaps where 5 volts is equivalent to 100% of our unit's intensity. And it is the digital pulse here which triggers the device, but the device has already been told at what intensity to rise or fall to. Configuring pulses. There's our single first digital output line. I've got 0, 1, and 2, so they're labeled as dig, and we have DAC. That's our digital to analog converter. So on the digital line, I would want to place a pulse at 0.2 seconds. That is my 0 time on this edge. Now, I had a little issue with this particular version earlier, placing a marker. And although that hasn't reported an error, I'm going to force one here. So there's a timing fault, and you can see timing fault shown here. So it's two items, two instructions that we're trying to call at the same time. Now, visually, they're not at the same time, but when we compile it, when we write the code to produce this output, they do appear at the same time. So something to watch out for. Now, I'm going to leave it like that just for a second. The marker is going to be writing to that digital channel we mentioned. And so it's going to be an indicator to me that we expected the TTL pulse to go out at that time, at 0. And so if I clicked it, I can get a code 00. So if I put another marker, a flag at the end here, and we put 01, we'll get a 01 for when the pulse goes back to 0. Okay, so let's start that. Run now. Let's make sure everything's connected and start. What did I do there? I think I might have been in the wrong mode, wasn't I? Pulses general fixed interval. Right. I think I must have missed something there. Pulses, outputs, vary. Okay. Fixed interval. Yes, that all looks fine. So if we start, we're expecting the pulses to come through. Where's my trigger? There we go. Right. So you can see on the left here that we have some digital markers. Okay. They're indicating the pulse going on and off. Now, I thought I had the digital output connected there. I'm not seeing it. So let's go back and just adjust those settings. So I had an x-axis. Oh, sorry, I'm still using ADC external convert. That's why. It's easy to miss. Start. There we go. Looking much better. Now you can see 0 and at 0.1, 2 markers indicating on and off. Now, using those for all of the stimulations that you're providing makes it much easier to do some online analysis. So, for example, we might set cursor 0 here. Let's get rid of cursor 1. Trying to cursor 0 active mode. I'm going to ask it to find the data points on the digital marker. And that's from the beginning to the end of the file or the frame. Okay, so there it is. It's always latching to this 00. I can ask it to find the next. As it moves, it can force other cursors to update their positions as well. So you imagine these 2 markers acting as 2 different stimuli. Cursor 0 will latch to them in turn once the frame has been captured. Other cursors could then surround an area just beyond cursor 0, and that could be a measure of peak to peak or area under curve. And at that point, we can start getting some measured output to XY views. Okay, so we've got fixed interval here, varying time. Now I think we want to look a little harder at varying everything else. So back into the configuration. General, we've looked at outputs. I really do want to come back to port setup and clamping in a short while, but the next thing I really need to show you is multiple frame states. So we've mentioned before the change in outputs, and that's what states are. So having multiple frame states enabled, the states tab becomes available, and I can set up n number of extra states, up to 256, so 255 of them. Let's set 3, and then let's go to the Outputs tab, which we've been becoming familiar with. Here, I'll just adjust this guy, and back into position. Now we've got state 1, state 2, and state 3. So these are alternative outputs. often in an experiment, we would not use the basic state. We tend to use it purely for monitoring data. So what I'll do now is copy everything I have in basic all the way through to the end of state 3. So that's all of the digital lines, all of the analog lines, control track, which means these markers and anything else I'd like to put in, as well as the fixed interval times, etc. I'll say OK, and now you'll see that all of these extra states are populated with the same. So I'll throw away what we had in the basic state. Come on, I'm just grabbing that icon and that one too. Right, so basic is without any outputs. Here we might set 2 outputs with an interval. What have we got there? 0.34 and 0.2. Okay, now one quick way of telling what's happening here is absolute times and absolute levels. Now we can switch between relative times and absolute times in the frame of output in the state. So configuring pulses again, 0.2, 0.34, let's just put that on the end to make it clear. State 2, we'll push this out a little further, and state 3, we'll push it out further still. Okay, so imagine a set of paired pulses. These could be accompanied by waveforms, such things as sinusoids, etc. Arbitrary waveforms even, placed onto the analog output lines. And let's say OK to that. And now I want to look more at the states. All right, now I've just had a question. Bear with me for a second. So it says, if you have a stimulator box that can be driven by either a digital or a DAC output, is there an advantage to pick one over the other? Well, if the stimulator receives TTL pulses, then I would prefer to use a digital TTL pulse to trigger it. It's much more robust, much more accurate in terms of timing than a DAC is. A DAC, although fast, still takes an appreciable time to rise up to the level you've asked, and that would be 5 volts. It then has to settle as well. So digital would be better for a digital input. Okay, I hope that's answered your question. I think I should qualify that a little more. So some devices, let's say Digitimer, I think the DS5 is both digital and analog controlled. So we could provide a sine wave to vary the current output, but I believe we can gate it, actually get the delivery of current passing only when the TTL pulse has gone high, stayed high and dropped down again. Okay. Right. Where was I? Right. Very quickly. States. We are now controlling we're changing the output, the types of pulses going to our other devices. And we can do that in a numeric, random, protocol, semi-random, or random repeated mode. Okay, so our 3 states, basic is not included, will be ordered in a numeric fashion. So it's in our output set now, we will have state 1 followed by state 2 followed by state 3. Okay. Now, if we go to random, we're simply throwing all of those labels for states up in the air, and then we're picking up each state in turn. Okay, and so we could have all the 3s together in one go. We then have semi-random, where if we take the number of states multiplied by the number of repeats, we will find that a random sequence of states will exist within each repeat. I think it'd be best if I show you that in a more graphical form in a few moments. Okay, right, so protocol. We go on to protocol here, then we have a fixed order of those states. So you might say that we wanted state 3 to repeat 5 times before we go where, and that is the next step. So let's say we want to move to step 3. So we've gone through this, state 3, repeating 5 times and jumping over to this step here, where we want state 2 repeating once before we go to step 2, where state 1 repeats 3 times before we might finish with a 0. Okay. Now, usually it's random output. And just to make that a little more interesting, we can ask for individual repeats. So now we're saying for state 1, maybe a single pulse, or in our case at the moment, paired pulses. I only want that to exist 5 times in the whole of our output. State 2, 10 times, and state 3, 15 times. So we've got a total of 30 outputs, and yet we've skewed the number of states within that output set. Here again, we have turn on writing with cycling and cycle automatically at start. So we're going to, if we have both of these enabled, we're going to go straight into the states outputs, not giving us a chance to look at the basic state and monitor EMG data perhaps right at the beginning. So I'm going to leave that off, but I do want to write. I want to make sure I am writing to disk whenever I go into my experiment proper. My experiment proper is the state variation. State variation here as a drop down. Dynamic outputs. That's pretty much always what you're going to use. The others are to either set up, that is static outputs, sending digital messages to another device, and perhaps to prepare that other device for a stimulus, and external digital, where we read digital inputs as a set of values and know which state to use next. So 99 times out of 100 dynamic outputs. Now, many of you will want to look at TMS devices added into this. And before we go there, there's one more question, which is, what is the purpose of the cycles before idle? Okay, so we might say that we want two sets of the states played out in random order. And when that finishes, the idle is where we jump to the basic state. And in our case, we have no outputs in basic. Okay, so basic is the idle. Does that answer your question? Okay, so where are we going? Oh, yes, adding devices. Right, in later versions of Signal, we can now have multiple stimulators added to the auxiliary device list. So we have MagStim, we have the Daymed Duo Mags, Power Mags, Mag Pro, Neurosoft, as well as our own current stimulator and Digitimer's DS8R. So let's look at a couple of these. Duo Mag to begin with, and we choose the type of device that we have available. Now, I don't have any of these devices in the room, but to set this up, I would need to decide whether I wish to use independent triggers. This is where we, the 1401, are providing the outputs to the stimulator for both the single and the paired pulses. Many of the devices already have a pretty accurate clock, and once they see a go TTL pulse, they can then time the 5 or 15 milliseconds to the next pulse to deliver. But if we wanted much finer resolution than that, then it's definitely better to use the independent triggers mode where available. If we had primary and secondary stimulator, we would see their names listed here, and then we'd move on to whether we wish to see the power of each pulse firing as a percentage of RMT. So we might know that the subject's RMT is 30% or 40%, we'd enter it here. And then for state 1, we would set the power to say 120% of RMT. For a DAMED Duomag device, we can set recharge delays. Now this is particularly interesting or useful when we're looking at EEG, so we don't have electrical interference. The second power here, let's say 140% of RMT, etc. Okay, now I can go into great detail there, but we will have a dedicated TMS session again soon. Now, forgive me if I don't add all the devices, but if we just hit a magnetic magstim here, different types, setting up for a single magstim 200 or dual magstim 200s. These are controlled through a serial line, which we can provide. Let's go for a bistim here. It would require us to input a COM port. Again, we're setting up the different intensities, and in this case, we can also set the interval for a state if we're not using independent triggered mode. So whenever state 2 fires, it has already set up the magstim and perhaps the duomag as well to be at these percentages. The magstim will then fire the second pulse after 5 milliseconds, and I think our duomag was set, let's say state 2 there. No control here for the second pulse because we're in independent trigger mode, you remember. So it is now these pulses in state 2, one pulse at 0 time, which is triggering the first A firing, and then some milliseconds later, I've exaggerated the distance here, for the second pulse for the B firing. Okay. Right, so we have our outputs, we have our states, we've set up some devices. Now, Signal is going to complain to me when we start sampling that these two devices aren't there, but at least we'll get some further output in a moment. I'll jump to automate, and here we might say finish our sampling when we hit the 30 frames. Remember, we had 5 frames for state 1, 10 frames for state 2, and 15 frames for state 3. So once we've gathered all of those, that's time to stop, isn't it? So let's set number of frames to 30. I've never ever used sampling duration, but I'm sure somebody out there has, and likewise file size. Well, that might have been useful when we were writing to floppy disks. Again, I don't find this as useful anymore. What I do find really useful are the file name, template, and path. So we could populate this with the day, month, and year, followed by a subject ID, etc. But essentially, we'd end up with something looking like that, where the 0, 0 would increment to 0, 1, 0, 2 for each successive recording we do. Okay, the path. Now this is where we put the data once it's saved. Okay. Now, one more thing before we get to a question there. Optimize y-axis for all channels at end of sweep. Well, that's useful. Okay, it's just going to show you the best view of the data. But if you're carefully trying to monitor an MEP, you don't want the data to be jumping up and down. Output resets, very useful. We might have stopped recording, stopped the system recording when outputs are still high, or in a state which might be detrimental to the rest of the experiment. So using output resets, we can bring everything down or set everything high, or any of the outputs individually. You wouldn't like to start sampling again only to find that we've sent a trigger pulse to the stimulator. for example. So this guarantees at sample start, sample finish, that everything is in a known state. Okay, so the question was, is there a reason you would not want to specify the number of frames? Well, you can continue on. So if we said number of frames, ignore this 30 limit, we might be hotspotting and wanting to store all of the data for later review. So we might easily go past 30 frames as the coil or the electrical stimulation, maybe to the neck here, is being repositioned. So you don't have to have a fixed number there at all. It just might be convenient to the operator to know that that's it, we've reached 30 frames. All right, so port setup, very quickly. If you've got our 1902 amplifiers, then we would have 1902 as a button here, and that would allow us to automatically set the gain for the channel based on the amplifier settings that we have. Now, in some parts of the world, it's no longer possible to sell the 1902, so an alternative may be the Digitimer D360 or the newer D360R, which should be available soon. Now, those types of devices also have a software connection with Signal, so we can read the amplifier settings and change the units, etc., for these ports accordingly. If not, if you don't have a device like that, you would want to use quick calibration, where perhaps I want to see my signal in microvolts, and I would set my total gain, let's say it's only 1,000. Okay, and that calculates what the full value would be at 5 volts input. Now that's the standard maximum range of the 1401. It is software changeable to plus or minus 10 volts if you wish. Okay, so you have quick calibration for amplifiers that we cannot communicate with, or if we have one that does, then we can get in and change the settings through here. For those people doing clamping, we might have the multi-clamp 700 or 900 device here, and we will talk about that in a second. If not a device, again, that can communicate through a known structure, then we might use the 41 telegraphs. Again, this is more for patch clamping. So depending on the level of an analog input, we could translate that to be the amount of current which is being delivered or the amount of voltage. Right. We'll go on to the clamp setting in just a moment, but we've set up our states. We should really start sampling. So no Duromag, no MagStim. Okay. Right. So I really think I should go and switch those off, because we have to be very careful about the safeties on these devices. Okay, let's get rid of this as well. Just run now. Okay, so no errors this time. We have a 0 position here, and we can start. Okay, so at the moment we're monitoring data. We're freewheeling. Basic is firing every few seconds, and we're just seeing whatever is connected at the end of port 1 and port 0 here. So here are some spikes. So if everything's okay, we will now move on to the ordering of states. Now I can do this in manual mode, where I can now say state 3, and I'm going to connect my digital output 1 AD one connection, and where are we? It's, yes, that one. So now we'll connect our I'll go to state 3. State 3 should be used next. Oh, right. Oops, right. Wrong output there. Yes, wrong output. There we go. So, state 3. If we cycle, then we should see that the states are showing up at the bottom of the screen and at the top here. It'll tell us which is the state to use next. So state 1 will come next. Okay, and I think I need to set. Am I? Have I frozen? Yeah. Back? Right, okay. Right, so now we should be seeing some proper variation. So, as I was saying, the ordering of states here. So you can see we're getting pulses and we're getting states when we do not get any pulses. Going back to manual, or allowing it to continue on to the 30 frames, we happen to have captured 19 so far. Perhaps I'm not showing my screen. Right. Okay, one share. Okay, better? Right, okay, so apologies for that. So we have the sequencing of the states. Now, let's look at, very briefly, some quick analysis. So virtual channels, create new. Let's assume that the center channel there is some EMG activity. So we might say absolute of channel 2, like so. And now we see a rectified form, which could be further processed to give you a smoothed version. Now that's important to use virtual as opposed to a recording directly a rectified waveform, because we can always go back to our raw in this case. If we record a rectified form, we can't put it back to its original positive and negative form, you see. Channels are coming in very useful there. They could also be used to describe something like this. So if I say I want to know when channel 2 was above 0.2 volts in this case, and I see a 0 and then a value of 1 for every time that we go above. There is also a duration, so we can see that the waveform has gone up and gone down again, whereas the second excursion here is lasting longer. Okay, now we can do more with that in the analysis session next week. Right, to finish off there then, we have then reached the maximum. We've hit 30 frames. We could continue on with more, and we could repeat individual states. So let's say state 3 had failed 3 times. Now, clicking on state 3 and continuing with more, and pause at sweep end, we can guarantee that we've got 1 extra state of 3, 2 extra states of 3, 3 extra states of 3. There we go. Right, all this time, I haven't mentioned the info windows. The ability to see from a distance what's going on. So perhaps a timer reading, start at reset, count time backwards, and we want to show this in seconds. Apply. Okay, as frames happen, we'll now get a timer reset and we're counting down. So very useful. These info windows could also hold information about measurements that have, in terms of TMS again, it might be the MEP amplitude that you've just measured. So you can see very clearly from a distance across the lab what the new value is, and perhaps even a difference between the current frame and the previous. Right. So we've got mostly the sampling functions there. If we're still sampling, which we are, then it is also possible to go and change the pulses on the fly. So I can now move my paired pulses, separating them like so, and apply. So next time I use state 1, there will be this new position for the second pulse. What else have we got to talk about here? Continue sampling. No, everything else is there within these controls. One item though, which I'd like to show you, is let's abort all of this, and let's just add in one of those stimulators again. I'll just use, say, a Mag Pro this time to give a bit of balance. Mag option. I don't really care that it's not used, and we run now. Okay, this time, as with all of the stimulators, you would have the ability to get back to the settings to be able to change controls for A and B pulses, as well as changing the percentage of RMT. So between sampling sessions, you can know the subject's RMT, enter it here, and then start. And everything will be referenced to this value here. Thinking of that, I have up here a sampling toolbar. I right-click, sample bar list. Here is a set of configurations. These are I appear to keep coming and going, but configurations that I have nothing. I'll continue then. Right. So here's a list of configurations for sampling that we have on our website as well. It's all for TMS in this case, but we'll give you a starting point. They're there. I've put them in the sampling bar list, and then I've enabled the bar by clicking here, which is sample bar. If I right-click on the grey area of spike 2, you can't see my screen at the moment. Just tell me. Can you see my screen? Yes. Okay. It appears to be blank, but if I hit one of these configurations, yes, there we go. So there's one. I can abort that. If I go to SICF, click that, you'll see that the outputs change, the layout of the screen changes, SICI, etc. Okay. So an easy change to a different configuration. Right, I think there is just a few moments that I'd like, I'm sorry to take up your time, we should mention clamping. Now, if clamping is not visible in the setup, the sampling configuration area, then we should come to Edit and then Preferences. And there you'll see Clamp, and we should enable use of patch voltage and current clamp features. I'll say OK to that, and we'll get onto the sampling configuration. Everything I've spoken about today with the outputs, randomization, etc., could still be applied. But patch clamp does require a little more setup. So from here, we would specify whether we're dealing with wholesale voltage or current clamp. we would then specify which is the stimulus channel, which is the control analog output, and which is the response channel. Now these channels are highlighted in red at the moment because their units are not correct. If we have a software driven amplifier, such as the Axon 700B listed here, then we would be able to access the clamping modes, membrane features, etc. And if you're really adventurous, you could go on to dynamic clamping. And this means that we could take in a data value and pass it through one of models like such. And the output of this is then passed to the next model, and so on and so forth. The result of all of this is that we pass back out of the DAC and back to the cell, representing current or voltage. And so therefore we can act as part of the biological network there. Okay, so close that, cancel, and I think through the skin of my teeth I just got through the majority of things that needed to be talked about. Signal is getting keep it streamlined for certain areas, and there's certainly hotkeys to allow fast navigation, for example, page up, etc. Page up, page down to step through frames in a data file. Tagging of frames, Control T, like so, to take them in and out of any analysis. There's a lot we can do with Signal. I hadn't even mentioned the text sequencer output, where we can decide whether to fire a stimulus because a waveform is above, below, or between thresholds, for example. So there's a lot more to investigate. Anyway, I will welcome any questions. Right, is there a way to select all frames in a data file? I guess you want to export, or you'd want to add all frames in the data file. Or do you mean that you'd like to see all frames in the data file? So if I went to documents and say signal 7 data, and we had actions, for example, okay? Now, I can set this to overdraw frames, and that is all of the frames overdrawn. I can look at overdraw settings and decide whether I want a subset of those frames, so a particular frame state, as we've just looked at. We'd also see this in 3D mode as well. Let's just look at this channel and bring up through the frames. There they are. Okay. Now, if you go to analysis, something like, let's do a waveform average in this case. Channel 2 here, width of average 2 seconds, a start offset, we'll leave it at that, new. Then we're asked all frames again. So yes, I mean, it's perfectly possible to say all frames, or when it, all frames. And when it comes to a script, that tends to be -1 as a flag to indicate all frames is what you want. Right. Part of that question is now, would we be able to select all of the frames to change the channel information for all of the frames? Okay. Do you mean then any information here, the title, etc.? I'm not quite sure I understand where you might be going with that. Okay, but certainly we can address all the frames, whether it means trying to do it in a stepwise order, step 1, frame 1, frame 2, etc. As I did yesterday, somebody was calling from, and inadvertently their markers were not in the correct position. Using us back into the correct position to represent 0 and say 100 milliseconds from that. Simply look at the frame with the script grab the data in the digital marker and then shift it across. Right, any more questions, anyone? I think, again, we've gone over time. Okay, so be quiet there. Right, I wasn't able to find the previous recording. I'm sorry, I've been a bit rushed. I'm still working on just doing an edit. It simply means taking off the beginning and end of the recording because there's a blank area, and then putting the questions onto the screen so everybody can see. But as soon as I've done that, it will be posted. We're holding them on YouTube for the time being on our own channel. But ultimately they will be added to our website, or at least links from our website as well. Right, please, yes, as Marjorie says, I was trying to write out, please email Marjorie and she'll make sure that she sends you the link when it's available. Okay. Right, if there's no more questions, then I think we'll call it a day. Thank you again for everybody for coming, and we'll see you hopefully next week for the beginning of the analysis sections. There we'll be talking about EMGs, MEPs, some patch clamping thrown in, virtual channels, and certainly active cursors. Okay. All right, well, thank you very much, everybody, and we'll see you the next time. Bye-bye.